Okay, so here's the familiar sledgehammer problem where, well, depending on what fair you go to, um, this game might be called Test Your Might, maybe, or I don't know, Strongman. But anyways, you hit a sledgehammer on a thing that makes a metal ball fly up. And so here what we've got is x is representing time, and then here this is the height of the ball. So after 4 seconds, the ball goes up and reaches a maximum point after 2 seconds, and then it comes down after 4 seconds. So before what we've done so far is we've found the average rate of change, for example, between 1 and 2. And we said that is called the secant line. So that line that's formed by those two points, this is called the secant line. Okay. So, but our goal is we want to find the instantaneous. So at that instant. Because that's the most useful one. So the instantaneous rate of change. Or for short, we're going to call it IROC. Dun, 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 dun. Okay. So let's say, for example, it's just to kind of think this through. Let's say we're looking for the instantaneous rate of change at x equals to 1. Now remember what we said is we can approximate the instantaneous rate of change by choosing two numbers that are close together. So if we find, for example, the average rate of change between 1 and let's see, the average rate of change between, for example, 1 and 1.001. What we said is that this is approximately equal to the instantaneous rate of change at 1. Okay, but we don't want to approximate anymore. We want to find the exact value. So what we want is we want to not choose 1 and 1.001. We want to get even closer. So we want to get so close that we're almost touching it, but not quite. And so basically, if you just kind of think of this dynamically, what you're doing is this guy right here, you're just going closer and 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 closer. And you want to get as close as possible without being right on top of each other. Well, what's the only way of describing that? The only way we have of describing something that gets closer and closer and closer without actually touching is using limits. So limits is the key to finding the slope of this tangent line right here, also called the instantaneous rate of change, and also called the derivative. So those three things, they're exactly the same thing. We're going to be talking a lot about those in the near future. But for now, just remember the derivative at a point, the instantaneous rate of change at a point, and the slope of the tangent line at a point are exactly the same thing. Okay, so let's do this. Let's write down a formula for the average rate of change, and I'm going to write it in a specific way. I'm going to write it between x and x plus h. Okay, so I'm going to draw this graphically here. So let's just say that this point right here is x, and then this right here is x plus h. Okay, so we're going to do this dynamically. Now let me ask you this. If those are x and x plus h, what's the distance between these two? Well, it would be h, right? Okay, so that makes sense. Okay, so now what this is equal to is f of x plus h, which is the y value right here, f of x plus h, and then minus f of x, right, which is this guy right here, all over x plus h minus x, which is just equal to h. Okay, now check this out. This is crazy. Awesome. Super duper. Okay, you ready? The instantaneous rate of change at the point x is going to equal to, I'm just going to rewrite this guy right here, f of x plus h minus f of x over h. Okay, now what do we do with that? What do we do with these 2 points? What we said earlier is we said, hey, let's bring this guy right over here, and so as this point gets closer and closer, this shrinks up. So where's h going? What value is h approaching if this guy keeps shrinking on to this one? Well, h is going to 0. So if we take the limit as h approaches 0 of this, the average rate of change, what we're doing is we're getting this guy as close as possible to this point without actually touching it. This would be impossible without limits. Without this idea of limits, we wouldn't be able to find the instantaneous rate of change. We can only approximate. So that's why we spent all that time talking about limits, because without limits, we wouldn't be able to find this. Now, that's basically it. So this right here is the instantaneous rate of change at this value x. Now, this is also the derivative of f of x, which is symbolized by f prime of x. So this is the derivative. And then also, we're going to do take a look at more notation. So I won't bother with more notation. We're going to see those later anyways. But this guy then can be used to find the instantaneous rate of change at any point. Any point. So later we're going to spend a lot of time learning a lot of tricks to simplify this situation, this derivative formula. But for now, this is the idea, and it's really, really important to understand the idea of how this came about and where it's derived. So now let's actually use this formula to find the instantaneous rate of change and the slope of the tangent line at 1. Okay, so what we're looking for is the instantaneous rate of change at 1. So also known as the slope of the tangent line at 1. And while we're at it, we'll find the equation of the tangent line as well. Might as well. Okay, so let me rewrite it as f prime at 1. So this is also known as the derivative of the function f at 1. So f prime at 1 is equal to the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. Okay, so this is equal to the limit as h approaches 0 of f of 1 plus h. So what this means is plug in 1 plus h inside of your function. So I'm going to have minus 2 times 1 plus h squared plus 8 times 1 plus h minus f of 1. I already know what that is. F of 1 is equal to 6. And just plug in 1 here, you get 6. Or you can just look at the table right there. Over h. Okay, so then I've got the limit as h approaches 0 of negative, if I FOIL this guy, 1 plus h squared, I would get negative 2 and then minus 4h. I'm also distributing the 2. Now, of course, you FOIL this first and then you distribute the 2. And then minus 2h squared. And then plus 8 plus 8h minus 6. All over h. Okay, so let's continue here. We've got the limit as h approaches 0 of, here I've got, let's combine like terms, 2 plus 8 minus 6, that's equal to 0. And then here I've got negative 4h plus 8h, that's 4h, and then minus 2h squared all over h. Okay, so then this is equal to the limit as h approaches 0. Now you'll notice that if you plug in 0 for h, you get 0 over 0, which is indeterminate, but that's easily solved because you can just factor out an h, and you would get 4 minus 2h over h. You get rid of those guys, and then after that, if you then plug in 0, notice that you'll get the number 4. So what this means, and this is in feet per second in this case, what this means basically is that exactly at that instant when when 1 second has passed, exactly at that point, the ball is going 4 feet per second. Much like your speedometer tells you how fast you're going exactly at that instant. That's what this is telling us. Now, later, this is just for that one single value, and it seemed like a lot of work, but later on we'll show how to find the derivative function itself, and a lot of easy ways on how to find the derivative function. And then you can just plug in the different values, and it'll give you the instantaneous rate of change at any point. So although this looked like a long and complicated process, we're going to look at a lot of ways to simplify this procedure. Okay, now let's do a little. Let's find the equation of the tangent line. So let's say if we're looking for the equation of the tangent line, we've got the slope already. We just found it. The slope is going to equal to 4. Okay, and so then we write down the usual y equals mx plus b. We plug in 4 for the slope, and then an x value and a y value. So I don't know about you, but I think well, we should plug in the only value that we know on the line, which is 1, and the y value is 6. So for that, you get that b is going to equal to 2, which, yep, looks pretty close to what our picture is showing there. And so then what this means is that our tangent line is going to look like y equals to 4x plus 2. And that's the equation of that tangent line. And that's it. So that's the derivation of the of the derivative. And so the idea is really important. Even though we're not going to use this method of finding derivatives much, the definition is super important, and understanding where it came from, how we got to this, is really important.